What would happen if you set foot on a planet where rain is made of glass, sharp as blades, slicing sideways through the atmosphere at 7,000 kilometers per hour? Or a world where a year passes in just 18 hours, and the surface is so hot that metal evaporates like water? This is not speculation. More than 6,000 exoplanets have already been confirmed, and each new discovery continues to break rules we once believed were obvious. These worlds are not just different from Earth. They are strange, violent, and profoundly counterintuitive, far beyond anything the human imagination was prepared for. Let's step into this journey together, where we are forced to confront the sheer wonder of the universe through some of the most extraordinary exoplanets ever discovered. First, consider one of the most extreme exoplanets ever discovered. No oceans, no clouds, no stable atmosphere. What remains is heat, radiation, and matter being torn apart down to the atomic level. Discovered in 2017, Kelt 9b is so hot that its daytime temperatures break apart molecules. It orbits its host star at a distance of only about 0.035 AU, nearly 30 times closer than the distance between Earth and the Sun. A full orbit is completed in just about 1.5 Earth days. Yet it is precisely this proximity that pushes the planet into a state that almost defies conventional definitions of existence. The dayside temperature of Kelt 9b reaches approximately 4,300 degrees Celsius, hotter than the surface of many red dwarf stars. At this level of heat, familiar molecules cannot exist. Chemical bonds are completely broken, leaving only individual atoms. When an atom loses electrons, it becomes an ion, and when trillions upon trillions of such atoms exist simultaneously, the planet enters a plasma state, the most common state of matter in the universe, yet one far removed from human experience. What happens when a planet can no longer hold onto its own atmosphere? Spectroscopic observations show that Kelt 9b is losing its atmosphere at a rate of about 100,000 tons per second. A massive stream of material is continuously blown into space, forming a trailing tail behind the planet, like a comet, but on a planetary scale. This is not a temporary phenomenon. It is planetary evaporation unfolding in real time. This process occurs as ultraviolet and X-ray radiation from the host star, a Type A star, far hotter and brighter than the Sun, bombards the planet. The immense energy continuously heats and expands the atmosphere until it escapes the planet's gravity. When gravity can no longer retain the gas, the planet begins to disintegrate. Kelt 9b does not generate nuclear fusion like a star. Yet its physical environment, temperature, ionization, plasma, resembles that of a star more than a gas giant planet. Where matter is not stable, not in equilibrium, but constantly transforming under extreme energy. Observations from space telescopes such as the Hubble Space Telescope, along with high-resolution spectroscopic studies, have confirmed the presence of ionized metals in Kelt 9b's atmosphere, a direct signature of this ultra-hot environment. But if a planet can become hot enough to break every molecular bond, what would weather look like on other worlds? If iron can vaporize, could it fall again as rain? A storm that doesn't soak you, but can cut through everything in its path. On WASP-76b, this is not imagination. It is a real physical cycle in motion. WASP-76b lies about 640 light-years from Earth and completes an orbit around its host star in just 1.8 days. Its extreme proximity has locked the planet tidally, meaning one side permanently faces the star while the other remains in endless darkness. This division creates a world split into two completely different extremes. On the day side, temperatures reach around 2,400 degrees Celsius, hot enough to vaporize not only water, but metals. Iron no longer exists in solid or liquid form. It becomes vapor, mixing into the atmosphere like an invisible metallic haze. The temperature difference between the two hemispheres, nearly 1,000 degrees Celsius, drives powerful atmospheric currents, pushing iron vapor from the day side to the night side at supersonic speeds. As this flow reaches the dark side, temperatures drop enough for the iron vapor to condense, and at that moment, something occurs that has never existed on Earth. Iron begins to fall from the sky. Spectroscopic observations from the Very Large Telescope have detected signatures of iron vapor on the dayside edge of WASP-76b, which disappear as the planet rotates into the night side, direct evidence of metal transport and condensation within its atmosphere. But if iron rain is enough to shatter our understanding of climate, there is another world where weather becomes even more violent. On HD 189733b, a planet about 64 light-years from Earth, the atmosphere appears deep blue, a color that suggests calm and serenity. But the reality is the opposite. Here, winds reach speeds of about 7,000 kilometers per hour, faster than any storm ever recorded on Earth. These currents carry silicate particles, the primary components of sand and glass. At temperatures near 1,000 degrees Celsius, these particles exist in molten or vapor form. And when swept into supersonic winds, they become a storm of absolute destruction. You would witness a rain of glass, not falling straight down, but driven sideways through the atmosphere at terrifying speeds. If you could stand in that environment, the sensation would not be getting wet, but being continuously eroded by countless sharp particles tearing past at supersonic velocity. Data from the Hubble Space Telescope has confirmed the presence of silicate particles in the atmosphere of HD 189733b. Through changes in light as the planet passes in front of its host star. On worlds like these, weather is the direct result of extreme temperature, immense pressure, and fluid dynamics in environments where matter is constantly changing state. Water no longer plays a central role. Metals and minerals take its place. And if a planet can turn its sky into molten metal, what happens when the planet itself can no longer hold its shape? when the gravity of its star begins to stretch and tear it apart. Perhaps metal rain is not the final extreme, but only a warning of something far more violent, a future where a planet is slowly being consumed, piece by piece, within its own orbit. There is no explosion, no clearly defined final moment, only a prolonged process in which each layer of matter is stripped away, each structural element torn apart in the silence of space. That is what is happening to WASP-12b, one of the clearest examples of a planet dying in real time. A hot Jupiter with a mass about 1.4 times that of Jupiter. Its orbit lies extremely close to its host star, only about 0.023 AU. At this distance, a full year lasts just 1.09 Earth days, and atmospheric temperatures can exceed 2,500 degrees Celsius. But what is truly destroying this planet is gravity. When a planet moves too close to its star, it enters a region known as the Roche limit, where the star's gravitational pull becomes stronger than the planet's own self-gravity. At this boundary, the object can no longer maintain a stable shape. The planet is stretched into a distorted form, like a droplet being pulled toward the star. Tidal forces create an enormous gravitational gradient across the planet. The side facing the star is pulled more strongly, while the far side is held more weakly. The result is a constant stretching of the entire planet, an unstable state sustained over time. But the process unfolds most dramatically in the atmosphere. Under extreme temperatures and intense stellar radiation, WASP-12b's atmosphere is heated and expanded. Combined with the star's gravitational pull, this gas can no longer be retained. It begins to escape, forming a massive outflow, a continuous stream of hydrogen, helium, and heavier elements being pulled directly into space. Ultraviolet observations from the Hubble Space Telescope have detected an extended envelope of gas surrounding the WASP-12 system, far larger than the planet itself. This indicates that WASP-12b is losing mass at an extraordinary rate, estimated at millions of tons per second. This escaping material does not simply vanish. Some of the matter falls into the star, while some is dispersed into space. The planet is not just losing mass, it is gradually dissolving into its surrounding environment. Notably, models suggest that WASP-12b could be completely destroyed within just a few million years, a remarkably short timescale in cosmic terms. That means we are observing it at an exceptionally rare moment, the final stage of a planet's existence. Here, as matter is no longer bound, as the atmosphere becomes a flowing stream, as structure loses stability, the boundary between planet and interstellar environment begins to blur. WASP-12b is not only being destroyed, it is being redistributed into its own star system. If there are planets consumed by light and gravity, could there exist worlds that operate in the opposite way? Places that do not reflect light, do not shine, but absorb nearly all the energy that reaches them. A planet so dark it consumes light, almost disappearing within the very universe it inhabits, that is TRES 2b, one of the darkest planets ever discovered, orbiting a sun-like star about 750 light-years from Earth. It belongs to the class of hot Jupiters, with a size comparable to Jupiter. Yet it orbits extremely close to its host star, only about 0.035 AU, completing a full orbit in roughly 2.47 days. But what makes TRES 2b truly remarkable is the way it interacts with light. Observations from the Kepler Space Telescope reveal that TRES 2b reflects less than 1% of incoming light, darker than coal, darker than fresh asphalt. It reflects almost nothing, absorbing nearly all the energy it receives. Why can a planet be that black? Unlike Jupiter or Saturn, where bright cloud layers reflect light efficiently, TRES 2b lacks reflective cloud layers. Its high temperatures prevent the formation of compounds like ammonia or water that would normally create bright clouds. Instead, its atmosphere contains elements such as sodium and potassium, substances that strongly absorb light in the visible spectrum. When starlight reaches the planet, instead of being scattered back into space, it is absorbed by these atoms and converted into heat. Under the faint illumination of its host star, it emits a dim red glow, like embers in the dark, not from reflection, but from its own heat, a form of thermal emission, weak but detectable by sensitive instruments. Studies based on Kepler data have confirmed the planet's extremely low reflectivity, along with atmospheric models indicating the absence of bright clouds and the presence of strong light-absorbing elements. If you could stand near this planet, the experience would be entirely different. There would be no reflected light from the surface. No sky brightened by clouds, only a vast, dark mass absorbing every ray of light, with a faint red glow radiating from its own heat. Here, light is no longer what allows us to see the world, it becomes something the world itself consumes. TRES 2b reveals a profound truth. Not everything in the universe is meant to be seen. Some worlds exist in silence, absorbing energy and leaving almost no trace. But if there are planets dense enough to swallow light, could there be worlds at the opposite extreme? It is far too light for its own size. That is Kepler 51b, one of the most puffy planets ever known. Located about 2,600 light-years from Earth, it orbits a young sun-like star, but what makes it extraordinary is not its position, it is its density. This planet has an average density of only about 0.03 grams per cubic centimeter. Lower than foam, nearly 30 times less dense than water, and even much lighter than Saturn, the least dense planet in our solar system. But how can a planet exist with such an incredibly low density? Kepler-51b has a mass only a few times that of Earth, yet its radius is nearly comparable to Jupiter. This means that most of its volume is not solid material, but an extended, inflated atmosphere stretching tens of thousands of kilometers into space. Studies suggest that Kepler-51b possesses a thick haze layer, a form of atmospheric mist made up of tiny particles, possibly containing methane, water vapor, and carbon compounds. This haze acts like a shield, absorbing and scattering radiation from the host star, slowing the rate of atmospheric escape. At the same time, the relatively moderate temperatures in this young star system help prevent the atmosphere from becoming strongly ionized, as seen in ultra-hot planets. Data from the Hubble Space Telescope also show that light passing through Kepler-51b's atmosphere is muted, a clear signature of a dense haze layer that obscures the chemical features beneath. If one could approach Kepler-51b, the experience would be unlike any other planet. There is no surface to stand on, no clear boundary between space and atmosphere. As you descend, the density of matter gradually increases, but never reaches a distinctly solid state. It would feel like floating within a vast ocean of gas, where pressure rises with depth, yet without a clear endpoint. Kepler-51b reveals that in the universe, a planet does not have to be a solid body or a tightly compressed gas sphere. It can exist as a delicate balance between gravity and gas pressure, a structure that is almost empty yet still persists. A puffy world today may become a stripped core in the future. This opens a different perspective on planetary evolution. Not all planets begin dense and then expand. This opens a different perspective on planetary evolution. Not all planets begin dense and then expand. We often think of planets as perfect spheres, a natural outcome of gravity pulling matter toward the center. But what happens when that gravitational force is no longer uniform? One of the clearest examples of this breakdown in shape is WASP 103b, a gas giant located about 1,500 light-years from Earth. On the side facing its star, the gravitational pull is significantly stronger than on the far side. This imbalance creates a gravitational gradient, a continuous stretching force that deforms the entire planet. Instead of maintaining a spherical shape, WASP 103b is elongated along the axis pointing toward its star, forming something closer to an egg or a droplet being pulled apart. This is not speculation. Observations from the Hubble Space Telescope, along with precise measurements of the light curve as the planet passes in front of its star, have revealed that the radius of WASP 103b is not uniform in all directions. The deviation is large enough to confirm that the planet is no longer spherical. But what is truly happening inside a planet like this? When gravity is uneven, internal pressure is no longer evenly distributed. Matter on the star-facing side is compressed more intensely, while the far side is effectively stretched and loosened. This creates an unstable internal structure, where layers of gas and material are constantly shifting, searching for a new equilibrium, a state that, in reality, may never be fully achieved. Here, the planet is not only geometrically distorted, it is physically transformed. Surface gravity is no longer a constant value. If it were even possible to move across such a world, an almost impossible scenario, gravity would vary depending on location. Near the star-facing side, it could be significantly stronger. On the opposite side, noticeably weaker. WASP 103b reveals that in the universe, shape is not a fixed property. It is the result of forces acting at a specific moment. When those forces change, shape changes with them, and if gravity can stretch a planet's very form, what happens to time when a world orbits too fast, too close, or too far? When a year no longer lasts hundreds of days, but only a matter of hours? On K2 137b, a planet orbiting extremely close to its star, a year lasts only about 4.3 hours. That means in the span of a single morning on Earth, this planet completes an entire orbit, an entire year passing almost instantly. According to Kepler's laws, the smaller the orbit, the shorter the period. And here, that rule is pushed to its limit. A planet racing through space at hundreds of kilometers per second, completing an orbit in less time than a single night's sleep. But when a year is compressed like this, it no longer carries seasons, no long-term transitions. Every cycle becomes rapid, continuous, almost blending into one. If it were even possible to observe from the surface, a nearly impossible scenario, the distinction between before and after would begin to disappear. In even more extreme systems, where planets orbit neutron stars, the ultra-dense remnants of supernova explosions, orbital periods can be shorter than 1 hour. A year is not just short, it becomes a moment repeating over and over again. According to the theory of relativity, time moves more slowly in stronger gravitational fields compared to regions of weaker gravity. This means that an hour on a planet near a neutron star is not the same as an hour on Earth. Time is no longer an absolute quantity. It depends on position in space, on the mass of the object, and on how space-time is curved around it. Here, a year is no longer a universal unit. It is simply the result of an orbit, a consequence of distance and gravity. Each planet carries its own rhythm of time, shaped by the environment in which it exists. There are worlds where a year lasts millions of Earth years, where a single orbit spans longer than human history itself. And there are worlds like K2137b, where thousands of years could pass in just a few of our days. Time, then, is not the fixed flow we once believed. It is a consequence of motion, a result of position within the universe. When distance changes, when gravity changes, when velocity changes, time changes with it. And when we look further, we begin to see that time is not the only thing that breaks. When orbits become more complex, when a planet no longer circles a single star, but is influenced by multiple gravitational sources, then not only years, but even day and night begin to lose their meaning. And can you imagine a sky where there is not just one sun, but two? Not rising and setting in a familiar rhythm, but two sources of light moving along complex paths, sometimes close, sometimes distant, sometimes appearing together, sometimes vanishing. A sky where day and night no longer have a clear boundary, where light does not come from a single direction, but from multiple directions at once. This is the reality on Kepler 16b, a planet orbiting two stars. Kepler 16b lies about 200 light-years from Earth, within a binary star system composed of one sun-like star and a smaller, dimmer companion. And Kepler 16b does not orbit each star individually, but instead circles this shared center, encompassing both stars within its path. This creates a complex dynamical system. Unlike our solar system, where planets orbit a single gravitational source, here the gravitational influence is constantly changing as the two stars move. But the most striking feature is not the orbit, it is the sky. If you could stand on a world like Kepler 16b, there would be no sunrise or sunset in the traditional sense. Instead, there would be sequences of complex light events. Two suns might rise together, doubling the intensity of daylight. Or one star could set while the other remains suspended above the horizon, extending the length of the day. At times, both stars set, plunging the planet into a darkness deeper than any night on Earth. Yet at other moments, one star begins to rise before the other has fully set, making night almost non-existent. The day-night cycle is therefore no longer stable. It shifts continuously depending on the relative positions of the planet and its two stars. A single day might stretch unexpectedly or end abruptly, with no fixed rhythm, no perfect repetition. And this leads to another consequence: extreme temperature variation. When both stars shine simultaneously, the energy received increases significantly. Here, a day may be longer or shorter than the one before it, depending on how the two stars move across the sky. But Kepler 16b is not unique. Observations from the Kepler Space Telescope have revealed many planets orbiting 2, or even 3, stars. The existence of these extraordinary exoplanets is not merely a collection of distant astronomical objects, it is a direct challenge to the limits of traditional scientific thinking. They remind us that the stability of our own planet may be nothing more than a rare exception within a universe filled with extreme variables. The journey of discovery is still unfolding, and as our instruments probe deeper into the vast darkness, we will come to realize that what we know today is only the beginning of a reality far greater and more mysterious than we ever imagined. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.